to 2015 exam question number 2. All right, so this is a time-consuming problem. So the allotted time here is 25 minutes, and I'm going to try to do it in less than that and explain everything. So let's just jump into it. So we have a battery. EMF is E. We're told that there's 3 identical light bulbs, all with resistance R. So they're equal resistances, and the switch is initially open. Now, as a student makes a prediction about bulb number 1. The prediction is about bulb number 1, about its brightness, and just the brightness of a bulb, it relates directly to power. So since they're talking about brightness here, brightness is power. The circuitry power equations, let's just put them up here. The one that's on the College Board equation sheet is P equals I delta V. But there's 2 other power equations, and the way you get those is by substituting in Ohm's law. Delta V, so obviously Ohm's law is delta V equals IR. If you substitute this in, you get P equals I squared R. And then if you substitute it in, the other way, so you could substitute, you could take Ohm's law, plug in for voltage, and then that gives you this equation. Or you could plug in for current. You rearrange Ohm's law for current, plug it in here, and then this gives you delta V squared over R. So we're gonna need these power equations, and we're also gonna need space. So let's shrink these down, and we'll kind of refer to these as we go through these questions. All right, so the first question is, when the switch closes, the student makes the prediction that bulb 1 will decrease in brightness. So I am going to say that we need to disagree with this. This is not true. When this switch closes, bulb number 1 is going to get brighter. Now, the reason for this, we're going to want to use this equation for our explanation. So with the switch open, when the switch was open, so my pen here does not have an eraser, so let me see if I go back. Oh yeah, okay, so with the switch open, basically what we have is 2 resistors in series. So when the switch is open, it's almost like you can take this part of the circuit right here and get rid of it. We have bulb 1 and bulb 2 in series, and the way you simplify resistors in series is adding them together. So with the switch open, the total resistance of the circuit would be 2R. Now, with the switch closed, when this switch closes, these 2 resistors are in parallel, and putting resistors in parallel lowers the resistance of the circuit. So let's diagram this over here. So with the switch open, when the switch is open, what we have is the battery, and then basically the total resistance of the circuit, adding these 2 together would be 2R. Now, when the switch is closed, what we're going to have is the battery, and the battery has EMF E. We're going to have we have this bulb number 1 first, and then these 2 resistors in parallel, they're going to simplify to R over 2, using the equation for simplifying resistors in parallel. So this gives a total resistance. Let's just combine these now. So R plus R over 2 gives 3/2 R. That's the total resistance of the circuit when the switch is closed. So the answer to this question is referring to this power equation right there, because we're focusing on bulb number 1. Bulb number 1 gets the current that comes out of the battery. Current comes out of the battery in this direction, right? Current is positive charge motion. Current comes through like that. So the current out of the battery is the current in these simplified diagrams here. So when the switch is open, current comes out, current goes through the whole circuit like that. So The current in bulb number 1 is the current out of the battery in both situations, open switch and closed switch. However, the current when the switch is closed, because this circuit here has a smaller resistance, 3/2 R versus 2 R, the current in when the switch is closed will be greater than when the switch is open. So, so our answer here for this first question is we disagree. Bulb number 1 is going to be brighter. The reason why is when the switch closes, the resistance of the circuit drops. Therefore, current out of the battery increases, which means the current through bulb number 1 will increase. And an increase in current, looking at our second power equation, an increase in current with resistance held constant will increase the power and therefore brightness of the bulb. Okay, now for calculation this second question, this is a little bit of work. So let's go to the second question. All right, so we need to set up some equations here. So before the switch is closed, the power of bulb number 1 is P1. So let's do switch open first. So the switch is open, and we need to derive an equation for the power of bulb number 1. So let's start by finding what the current would be. So, our simplified circuit for when the switch is open, we have bulb 1 and bulb 2 in series. So that's going to give a total resistance of 2R with a voltage of E. Now, if there's only one resistor, so let's just say, for example, this is a 12-volt battery to make up an example. So if that's a 12-volt battery, positive terminal will be 12, negative terminal will be 0. Right here would be 12, right here would be 0. Because remember, EMF, it's another name for voltage, which is the change of electric potential from one point to another. So, so the voltage across our simplified resistance is 12. So using Ohm's law, voltage equals IR. So the current here is going to be voltage over the total resistance, and the total resistance is 2R. So this is our current. This is our current when the switch is open. So let's just circle that. Now, when the switch is closed, the circuit becomes this. So it all simplifies down to bulb 1 in series with 2 and 3 simplified. And as we said earlier, that's going to simplify to 3/2 R. So using Ohm's law again, current is going to be the voltage across the resistor, the simplified resistor, divided by the total resistance. So this is going to be voltage over the total resistance, which is 3/2 R, and this gives a current of 2/3 R. Now keep in mind, what we calculated here is the current coming out of the battery. So let's call this guy I2, and we'll call this guy I1, right? So the current out of the battery is the current through bulb number 1. So as we said in the first part, there's going to be a increase in current. This is 1/2 E over R. This is 2/3 E over R. So when the switch closes, there is an increase in current through bulb number 1. Okay, now let's do our power equations. Because for question 2, what we're trying to do here is we want to come up with some equation where when the switch closes, we're calling it P new, and we want this to be something times P1, where P1 is what the power of bulb 1 was before the switch closed. Okay, so let's first of all solve for what P1 is. So P1, which is the power of bulb 1 before the switch closes, is going to be equal, we'll use this power equation, I squared R, where the current through bulb 1 was E over 2R squared times R. So this is going to simplify to, oh man, this is going to be E squared over 4R squared times R, which is going to simplify to E squared, so one of the R's cancels, over 4R. So let's put a circle around this. This is P1, which is the power of bulb 1 with the switch open. Now, the new power, when the switch closes, the current changes. So over here, we have the current through bulb 1 when the switch closes. So again, using I squared R. However, the current now is 2/3 R squared R. So this is going to simplify to, this is going to be 4, oh, I forgot the E. 2E. So this is going to be 4E squared over 9R squared times R. One of the R's cancels again. And this is going to give us 4/9 E squared over R. So we're almost to the answer. So now what we got to do is get a common denominator of these two equations. Let's get rid of this. Okay, so the common denominator here is 36. So this one here is going to be 9/36 E squared over R. This one is going to be 16/36 E squared over R. So with everything else being equal, aside from the 9 and the 16, we can see that the power of bulb 1, P new, is greater than what the power was when the switch was open, which was P1. So how much greater? Well, P new is going to be 16/9 what P1 was. The relationship here is that this is larger than this. By how much? By 16/9. So this is the answer to the second question. And then I love these questions here. The third question, how does the result of part 2 relate to your explanation in part 1? It basically confirms our answer for part 1, because what we said in part 1 is the brightness of bulb number 1 will increase when the resistance of the circuit goes down, and therefore current through bulb 1 goes up. So the answer to this is that our calculation in 2 confirms our answer of 1. Okay, now before we go to the next part, we're going to be using some values like the currents. So current, when the switch was open, I'm going to be using this, and I'm not going to go through the whole entire derivation again, but this is the current. This is the current in bulb 1 when switch is open, and then we also found the current in bulb 1 with switch closed equal to 2/3 E over R. So we did that prior. So that's the current in bulb 1 when the switch closes. So let's revert this and let's keep going. Okay, part B. Okay, so now we have another student making a prediction. Student makes the following prediction about bulb 2. So when the switch closes, bulb 2 will decrease in brightness. I'm going to agree with this. So the power equation we want to use here, I think the nicest power equation to focus on in this answer is P equals delta V squared over R. So again, when the switch is open, with the switch open, we have bulb 1 and bulb 2 in series. Now what that means is if the resistances are equal, So resistances are equal. So again, let's just say it's a 12-volt battery. Oops, not so 12-volt battery. So that means, you know, positive terminal is 12, negative terminal is 0. So right here would be 12, right here would be 12, over here would be 0, right there would be 0. So as the current goes through these bulbs, if these resistances are equal, this 12 volts is going to be lost in 2 equal chunks across these resistors. So the voltage across this guy would be 6, the voltage across this guy would be 6. It'd be equal. So okay, so that would basically be in terms of the given variables. So in terms of the given variables, we could say switch open, the voltage here is equal to E over 2, and then the voltage here is E over 2. This voltage gets split equally. Okay, now when the switch closes, this is no longer going to be true. And the reason why is the voltage across these bulbs will be less, because when you put resistors in parallel, that lowers the overall resistance. So let's put this into calculation. Well, let's just go ahead and give the answer to 1, and then I'm going to verify it with a calculation in part 2. So the answer to part 1 of this question is we are going to agree that when the switch closes, bulb 2 will decrease in brightness, and the reason why is the voltage across bulb 2 is going to drop. And we want to reference this power equation, delta V squared over R. There is a decrease in resistance across these, there's a decrease in total resistance from that point to that point. The resistance drops, and therefore the voltage will drop. More of the voltage will be across bulb number 1, less of the voltage will be across bulbs 2 and 3. Okay, now let's prove this with a calculation. Okay, so let's look at switch open. So switch open, focusing on bulb number 2, so we're going to focus our calculation on bulb number 2 here. Switch is open, let's use Ohm's law. So the voltage the voltage across bulb number 2 is going to be the current multiplied by the resistance. Now we already know what this current is. We calculated it in the first part. Current through this circuit when the switch is open is equal to E over 2R. We did that in the first part. Times R. R's cancel, E over 2, which makes total sense because bulb 1 and bulb 2 are sharing the voltage of the battery. So voltage across bulb 2 would be E over 2. Voltage across bulb number 1 would also be E over 2. Okay, now when the switch closes, that's going to change the current through bulb number 2, and therefore the voltage across bulb number 2. So earlier in part A, we calculated that when the switch closes, the current coming out of the battery through bulb number 1, when the switch closes, that current is going to change to 2/3 E over R. So we did this calculation already. So that's the current. 2/3 E over R is current when switch closes coming out of the battery. Now right here, that current is going to split. This 2/3 E over R is going to split, which means half of it goes this way, half of it goes this way. So if we take 2/3 E over R, divide it by 2, it becomes 2/6 E over R, which is 1/3. So the current, when the switch closes, current coming through bulb number 2, this current right here going through bulb number 2 is going to be 1/3 E over R. So now let's calculate. So when switch is closed, and again, we're focusing on bulb number 2, the voltage across bulb number 2 is going to be, so we're doing I times R. The current through bulb number 2 when switch closes is 1/3 E over R. So we'll just put E over 3R times R. So R cancels and we get E over 3. So what that tells us is 1/3 of the voltage of the battery is across bulbs 2 and 3. Because remember, when resistors are in parallel, they always have the same voltage. So 1/3 of the voltage of the battery is across bulbs 2 and 3, which means 2/3 of the voltage of the battery is across bulb number 1. Okay, so let's put this into power now. So with the switch open, so this is, we're focusing on bulb number 2. So for switch open, power is voltage squared over R. So when the switch was open, voltage across bulb number 2 was E over 2, right? That's what we have right here, squared over R. And then that is going to simplify down to 1/4, basically 1/4 E squared over R. 1/4 E squared over R. Now, switch closed, using the same equation, delta V squared over R. So the voltage with the switch closed, that was E over 3. So this is going to simplify down to 1/9 E squared over R. So we justified this. What we can see is that when the switch is closed, the power of bulb number 2 is significantly less than the power of bulb number 2 when the switch is open. So these are the calculations that would verify it. We see that power with the switch closed, power of bulb 2 smaller, and then when compared to when the switch is open, the power is greater. Okay, last part. Okay, no. Yes. Okay, so here's part C. So now, well, the switch is open, bulb 3 is replaced with a capacitor. So let's get bulb 3 out of here. Let's see, why did that not? It's not letting me delete. Okay, let's just scribble over it. So bulb 3, we'll just scribble in a capacitor. Bulb 3 is replaced with a capacitor. Okay, and it's uncharged. So the switch is then closed, and as with all capacitor questions, the two situations are immediately after the switch is closed, and then the other situation is a long time after the switch is closed. So whenever you're doing problems like this, you want to start by focusing on voltage. So again, let's just say that this is a 12-volt battery. 12 on this side, 0 on this side. Now, if this capacitor has no charge, that means there's no voltage across it. So the fundamental definition for capacitance is charge over voltage. So rearranging this for voltage, we get charge over capacitance. The capacitance of this capacitor is going to stay constant, but the point here is if the capacitor has 0 charge on it, that means the voltage across it must be 0. So let's follow our volts. So starting at the battery, 12 volt on the left, 0 volt on the right. Right here is going to be 0. Right here is going to be 0. In fact, right there would be 0. Right here is 0. Switch closes. Now the capacitor is not charged yet, so right here is going to be 0. And then even on this side is going to be 0. How do I know it's 0 on both sides? Because there is no potential difference across the capacitor if there's no charge on the capacitor. Okay, so right here would be 0, right here would be 0, right here would be 0, right here would be 12. The moment the switch closes, all the voltage is across the first bulb. There is no voltage across the second bulb because we have 0 volts on both sides. Okay, so how does the brightness of bulb 1 compare to the brightness of bulb 2 immediately after the switch is closed? Well, I think the easiest way to answer this first question is simply by saying when the switch is first closed, all of the voltage of the battery is across bulb number 1. There is no voltage across bulb number 2. So you could use the power equation P equals delta V squared over R. If bulb number 1 has all the voltage and bulb number 2 has 0 of it, that means bulb number 2 is off and bulb number 1 is very bright. Okay, second question. So now same thing, but a long time after the switch is closed. So let's draw in a capacitor here. Here's a capacitor instead of a bulb. Okay, so switch has been closed for a long time, which means the capacitor is now fully charged. If a capacitor is fully charged, when the current comes out of the battery and then comes around like this, if the capacitor is fully charged, we will not get more current going up here. This will not happen because the capacitor cannot take more charge. And also realize that a capacitor is a break in the circuit where the current cannot flow through. So long story short, if the capacitor is fully charged, the current is going to go through bulb 1 and bulb 2 in series, because there will be no branching. And what's the question? How does the brightness of bulb... Oh, right. So we're comparing the brightness of bulb 1 and bulb 2. They're going to have equal currents and therefore equal voltage because the resistances are equal. But, you know, I would just go P equals I squared R. The resistances are equal. The current is equal because no current goes to the capacitor. So therefore, both bulbs have equal brightness. All right. Okay. Almost done. How does the result of your derivation... Oh, okay, so this question here is going back to question A, part 2. What do they have us? Before the switch is closed, the power is P1. So this question is getting at, so the question we answered in part A 2 hinged on current, which, and our answer here, I think it's a great way to go to answer it based upon what happens to current. If current is equal in these two resistors, then the brightness must be equal.